few more applications of Faraday's law. Generator. This is a makeshift generator. Probably all seen these, the flashlights that you shake. Little magnet, there's a coil here. The magnet moves through the coil as you shake it. There's a setup of some capacitors in here, some resistors, I don't know what else. Shake it for a while, that charges the capacitor. Turn it on, you have a nice little flashlight. Works great. General setup of a generator. So the generator that you would want to generate electricity, say, in your home. This is a very crude simplification, but we're just trying to get the main picture aside. So there's some permanent magnets. We have a north pole facing a south pole. And inside the magnets, we actually have a coil. We're not going to worry how that coil hooks up to the circuitry. You can change whether you have an AC generator or DC generator, how you hook that circuitry up. Now we know from Faraday's law that we can induce a voltage in there and thus induce a current in there if we can make the flux change. Now, in a generator, we don't swap out the magnets, so we don't make the magnets stronger or weaker. So the actual magnetic field is not changing. The size of the coil isn't changing. So how can we change the flux?
Spin the coil.
Spin it. As we change its orientation in the field, that will change the flux. We know the magnetic field...
Or the magnets.
Yeah, you can spin the magnets as well. The magnetic field is pointing north to south. We know flux, magnetic flux. In this case, the field is pretty much uniform. So we know the flux is simply B dotted with A. But the dot product, that means you're multiplying just parallel components. With the way I've drawn it right now, none of those field lines could pass through that area. The maximum flux would occur if I could orient my coil this way, so all of the magnetic field lines are passing through it. So as we turn the coil, the angle between these changes. If you happen to remember, we can write the dot product as the magnitude of the two vectors times the cosine of the angle between them. By changing that angle, we're changing the flux. So we're not changing the strength of the magnetic field, we're not changing the strength of the size of the area, but we're changing the area, the angle between them. And so that changes the flux. This angle, the angle between them, is directly related to how fast that's spinning. Been a while, but if you remember rotational motion, we have kinematic equations. Assuming it's rotating at a uniform rate, theta would simply be omega, the rate at which it was rotating in radians per second, times the time. So we can write our flux as B A cosine of omega times time. Omega is the angular frequency. It's measured in radians per second. So coming up here, the induced voltage is going to depend on how many turns we have in that coil, how many times the wire wraps around. And it's going to depend on the derivative of this function with respect to time. Derivative of cosine is negative sine, so the negative signs will cancel. The B and the A are constants. Derivative of the inside stuff is omega. So our induced voltage, if you want to put the omega in front, WMVA.
Like the bar.
The induced voltage depends upon the number of turns we have. It is dependent on the strength of the magnetic field, the area of your coil, and how fast it's rotating. The maximum value. So the way we have it set up, this is an AC generator. So it's creating an alternating voltage, which would create an alternating current throughout the circuitry. What is the maximum value of the voltage that's induced? Right. Everything in front of the sine term. So N, the number of turns, B, the strength of the field, A, the area of your coil, and omega is the rotation rate.
E RMS is MVA omega over root 2.
Yes, it will be.
We can never talk about alternating current.
Briefly, that's our last chapter, is alternating current circuits.
Keep saying in my head.
All that means is the current alternates.
Why do they do that? Travels farther.
The AC transmits a lot better and a lot further easily.
And transformers don't work without AC.
And that's a good point too. Transformers will not work unless you have AC.